Lesson 1.3, Task 1. All right, so it says translations of function graphs. In previous courses, you performed transformations of figures and function graphs. Different transformations are indicated in a function rule by different parameters. A parameter is a constant in a function rule, such as a or b, and y equals ax plus b, that can be changed. All right, so that's just your slope-intercept form, and a and b is your slope and your y-intercept, and those numbers can be changed. So a and b is just a constant, which is a number. Each graph below shows a graph f of x in blue and a function g of x in red, formed by translating the graph of f of x. To the left of each graph is a mapping diagram of the input and output of f and g corresponding to the graph. All right, so you can see this function says g of x equals, so g of x equals f plus 2. So f of x plus 2, and that gives you g of x. So the input for g, negative 1, 1, 3, 5, negative 1, 1, 3, 5. So the inputs are the same for g and f. And then the output for f is all 2, let's see, negative 2, 2, negative 2, 2. And the output for g is plus 2. So 2 more than all of these for f. So these numbers are each 2 greater than these. So when you graph these, you can see the blue line is the original function, or f, and the red line is the transformation, or g. All right, the bottom one, this one is a little bit different. This one's inside the parentheses, so the negative 2, so it's x minus 2 is inside the parentheses. So g of x equals f of x minus 2. All right, so here you can see that the inputs of g and f are different. Okay, so the inputs for this one have been you subtract 2 to get the input for f. All right, and you can see that this one is a horizontal translation. So this one was a vertical translation. This moved you up or down, and this one moved you left or right. All right, so let's see what the questions say. Compare the mapping diagram of graphs f and g in the top row of the table. Which statement best describes how the inputs and outputs of f and g compare? All right, so in the top row, that's this one right here, how did these compare? So the inputs were the same, the outputs were 2 greater than. All right, so it says each input for g is 2 more, each input for f is 2 more. The inputs are the same, okay, so that's what we're looking for. The inputs are the same, but the outputs are different. All right, so the inputs are the same, and for each input, the output of G is 2 more than the output of F. So that is the correct one. And this one probably just reverses F and G. But if you remember, above F is the original function, G is the transformation. All right, so what effects does the parameter 2 in the rule g of x equals f of x plus 2 have on the graph of x? Well, it shifted it up 2 units. So this is left, right, down, up. So it translated the graph up 2 units. And you can see that in this one. You can see from the blue graph to the red graph, it just moved each point up 2 units. All right, compare the mapping diagram and graphs for f and g in the bottom row of the table. Which statement best describes how the inputs and outputs of f and g compare? All right, so the bottom row is this one. So for this one, f is 2 less than g. So for getting ahead of myself. So for this one, the input is different and the outputs are the same. So the input of f is 2 less than g. All right, so this one says for each input of g is 2 more than the corresponding input of f, and the outputs are the same. All right, each input of f is 2 more than the corresponding inputs of g, and the outputs are the same. All right, so is it G or F? All right, so the input of G is 2 more than F. All right, so it says, what effect does the parameter 2 in the rule G of x equals F minus 2 have on the graph of F? All right, so this time it moved it horizontally, and you can see that it moved it from the blue line to the red line, so it shifted it to the right. All right, so the second one says it translates the graph of F right 2 units. This one says left, down, and up. We're looking for the one that shifted it right. All right, in part A, adding 2 to the output values of F translates its graph in a positive vertical direction on the coordinate plane. Remember, in the first one, it moved it up or down depending the sign. In part B, subtracting 2 from the input value of G to obtain the input value of F translates the graph of F in a horizontal direction. How does moving the parameter 2 from outside to inside the function result in this difference? All right, so anytime it's outside the parentheses, like here, it is going to be a shift on a horizontal movement. It's going to be a change in Y's. Here, it's going to be a change in X's, so it's going to be horizontal. And this time, when it's inside parentheses, it's always opposite of what you expect. When you see negative 2, you think it would shift left 2, but it actually shifts right 2. And so if this was X plus 2, it would actually shift to the left. So there's several functions in math where when a number is inside of parentheses, it actually does opposite the sign or opposite the direction you think it's going to go. So this one shifts it up 2 when it's plus 2, down 2 when it's minus 2. This one shifts it right when it's negative, and it shifts it left when it's positive. All right. If you have any questions on task 1, please let me know. Lesson 1.3, task 2. Stretches and compressions of function graphs. While a translation of a graph of a function affects only its position on the coordinate plane, a vertical or horizontal stretch or compression affect the graph's appearance. Each graph below shows a function f of x in blue and a function g of x formed by stretching or compressing the graph of f of x in red. To the left of each graph is a mapping diagram of the inputs and outputs for f and g corresponding to the graph. All right, so if we look at this, we can see g of x equals twice f of x, so 2 times f of x. All right, so for our inputs, we can see that the inputs are the same, and we can see that the output of f times 2 gives us the output of g. Okay, so what does that look like visually? We have the original function in blue, and we can see that each value here, 2 times 2 is 4, and 2 times negative 2 is negative 4, so it's multiplied each of those values by 2. Okay? All right, so g of x equals f times, in parentheses, half x. Okay, remember there's a difference when it's inside the parentheses here. So this is going to change the input values instead of the output values. All right, so the input values of g are here. And then if we multiply the input by 1/2, we get the output values. And we can see that 5 is half of 10, 3 is half of 6, etc. So these are just each 1/2 of this. All right, then we look, and the outputs are the same. Okay, so look at the graph. The original function's in blue. And you can see that it has stretched this by a factor of 2. So it's kind of opposite of what you think because, again, it's inside the parentheses. Always kind of does a little bit different of what you think it's going to. All right, so let's see what the questions say. Compare the mapping diagram and graphs for f and g in the top row of the table. Okay, top row of the table. Inputs are the same. Outputs are multiplied by 2. So f times 2 equals g. All right, so the inputs are the same. And for the given input, the output of F is 2 times the output of G. Again, F times 2 equals G. So G is 2 times the output of F. See, we're taking F, we're multiplying it by 2, so you just got to be careful with the wording. The inputs are the same, and the output of G is twice F. All right, so what effects does the parameter of 2 in the rule g of x equals 2 times f of x have on the graph of f? All right, so it says it compresses, it stretches. All right, so it stretches the graph of f vertically by a factor of 2. So that is true. And then the next one says compare the mapping diagram and graphs for f and g in the bottom row of the table. Which statement best describes how the input and outputs of f and g compare? All right, so again, look at the bottom one. We're going to see that the inputs are different. So g times 1/2 equals f. So f equals half a g. All right, each input for f is 2 times the corresponding input for g. Each input for g is 2 times the corresponding input for f. So it would be the second one, I believe. So g, 10 is twice 5. So the input for g, each input for g is 2 times the corresponding input for f. Again, I look back to C, and where you see 10 is twice 5, you know that that's twice as big. 5 is half of 10, or 10 is twice 5. All right, so what effects does the parameter of 2 in the rule g of x equals f times 1/2 x have on the graph of f? All right, so it also stretches the graph f horizontally by a factor of 2. All right, so again, you can see that this one, when it's outside, when it's in front, the number's in front of f, it's going to stretch it vertically, and here the number 1/2 x is going to stretch it horizontally. All right, so in part A, multiplying the output value of f by 2 stretches its graph vertically. In part B, dividing the input value of g by 2 to obtain the input value of f stretches its graph horizontally. How does moving the parameter 2 from outside to inside the function result in this difference? Okay, so very much like in the last task, when it's outside, it's going to move it vertically, and when it's inside, it's going to move it horizontally. Okay, if you want to see a sample answer, let's see what it says. It says your input value into a function, obtain an output, and then multiply it by 2. It simply multiplies the y value by 2. If for the same output value, you must divide an input of g by 2 to obtain an input of f. It means that the input value of g has to be 2 times the input value of f. Since the x-coordinate indicates the input, this means that the graph of g will be the graph of f stretched horizontally by a factor of 2. All right, so that is the mathematical explanation for that. All right, so if you have any questions about task 2, please let me know.